So thank you so much. I just want to start by thanking the organizers. Lucca is just a beautiful place. So even though it was far away, we decided to come just for the folks who are here and the place itself. So thank you for your hospitality and the time you've given us. So Chris has covered some aspects of it already. So there's going to be some repetition, but I'll hopefully be able to speed up as well. We had given a couple of tutorials, one on synthetic information systems that folks can download, take a read at it, and also I've given now 3 tutorials on epidemiology and public health. That's also there online. You folks can take a look, and actually covers most of the things that I'm going to talk about today. And the links are in the slide itself. So I want to start by simply saying that we want to do, the question that was asked in the morning was, how do we try and support the questions related to pandemics and pandemic preparedness? And I think that building tools, models, systems, one has to do it in a way that goes beyond predictions and tries to reason about these systems and reason about situations and actions, as the phrase Chris had used. So the idea is to build a set of tools that allow you to synthesize different data sets. We had talked about it today morning as well, provide range of interpretations, evaluate the responses, monitor the effect of these responses, and then support coordination among stakeholders. So this goes really beyond prediction. There's a very nice article in Science by Feinberg and Harvey on epidemic science in real time. It's really the focus of my talk today. So just to give you a sense for the work we had done, Chris again mentioned this, but I want to take as an example the work that the group did. And just like Bruno said, the work that I'm going to talk about throughout my 10 minutes is not the work that I've done alone, but really with a group of wonderful folks, collaborators. And a particular project that I think was quite successful, I would say, from an analytical standpoint for us, is the work the group did in supporting the DoD in terms of Ebola response. We were the lead analytical agency for one of the DoD groups and worked with them very, very closely in trying to answer questions related to Ebola response in West Africa, questions related to estimating the epidemiological parameters like Bruno had talked about, to forecasting ongoing pandemics, to assessing the threats, locating emergency treatment units, estimating the need for supplies. We also studied social media and its role in it. Turns out that it does not have that big a role in West Africa because of the lack of use of social media then. That doesn't mean it won't be that way. And much of the data and the studies and analysis are available on web. And I'll say a little bit at the end what this all entailed, but we actually did over 30 presentations. Brian Lewis led this study in our lab. And this was done with great care, where we had a lot of interagency groups working with us closely in presenting and answering the questions that were raised here. So the question that was raised was, how does HPC help in doing this? So my answer is that HPC helps in a range of different ways in pandemic preparedness and responding to it. So I'll start with the first one that Chris talked about, which is synthesizing data. We've done this now over a period of 20-25 years, where we've taken very diverse set of data sets, approximately 40 different data sets, to build large-scale synthetic information systems. These are network representations of the systems that allow you to study various dynamics. The specific ones that is of focus today is diseases. Chris has showed you the slide. We have now created a synthetic system for the entire globe. We can simulate this diseases on these networks rather rapidly. And I want to say a little bit more. Chris went through it faster because I think this is a focus of the talk today. When we started this work back in 2000, 2001 for this particular topic, the earlier work on transportation started even earlier, we could simulate a city of size of Chicago with 10 million nodes and about 500 million edges. It took us between 24 to 48 hours to do a single run of a flu season on a system which is around maybe 150 to 200 cores. Now, we can actually do this in less than 10 seconds, and the largest machine that we have mapped this is a 750,000 core machine, which is at NERSC. We just got a award from the NERSC folks for innovative use of petascale machines for social science applications. And it's probably the largest social science application that has been mapped on a system like this. The reason I bring it up is of the conversation we had yesterday. This is one interesting application for exascale machines. And I think we are fairly well set up to try and use these machines effectively. This requires a lot of skills to get these applications to scale up to this size. They are not typical machines to work with. We have also then tried to send the results from these systems out to folks, and the paradigm that we are using is providing X, where X is either software, data, simulation, analytics, as a service. We again talked about it today quite a bit in the early session, so I won't delve into it too much, but really providing the service is the best way to describe the work that we are doing. We have built multiple tools that are there on our website. Please take a look. Tools that relate to situation assessment like Eyes on the Ground, to forecasting tool called Epicaster, to MyForesight, which allows you crowdsourced ways to predict, to a system called Sybil, which is a very, very interesting planning and response tool that DoD has been using now for the last 9 to 10 years in terms, and 30 plus case studies have been done using the system. What I want to quickly highlight in the use of computation here is not just doing structure analysis, which is the left side of this panel, but going from structure analysis all the way to coevolution, which makes the problem progressively harder and harder in terms of the mathematical models one use. I think something we should keep in mind. There's a particular project that we finished recently, but is still live. It's a project called Embers that was funded by IARPA to forecast social, political, public health events as a big data system. Very, very successful project. We took a lot of input data and tried to predict events in South America, from unrest to the problems around the soccer games in Brazil, to elections in Venezuela, to flu, seasonal flu forecasts in all these countries. Used a number of statistical and machine learning style models to causal models as well in this setting. So let me end with 2 slides and then we'll be done, and gives us time to discuss and have questions. But I think the role of computing is important in all this. And Guido, you had asked about and talked about this. We also think that networks is a very interesting representational theory, and it actually is very closely tied to computing itself. And Roberts talked about it too. It's a representation that is suited for today's technology. It is a representation people knew maybe 100 years back, but couldn't do much with it beyond simple examples on a paper and pencil. The role of computing is important, but also role of algorithms. And algorithms not as Turing machines, but semantics of these distributed systems become important. Autonomy, and I call it 3 Ps of systems: pervasive, personalized, and precision become important. So let me close with what we learned during the last 10 to 11 years when we tried to support pandemics such as the H1N1, planning for H5N1, Ebola, SARS. We also worked on Zika. And here are the things that we have learned over a period of time. First is the very delicate balance between doing rigorous science and real-time response. If the pandemic is really, ongoing phenomena, then you cannot wait to say that I'll take 4 months to come and give you the best answer. You have to produce answers that make sense in the time you've been given and hopefully try and refine it. This becomes complicated, and in my slides I have a modified theorem from Tukey. I modified it for our purposes because it says that you need a model. Having a perfect model is not as useful as having a model that suffices for the question that you are given in the time. Role of individual and collective behavior is important. Data sharing and access and making it computer readable is a challenge, and it's very, very important during such settings. It's hard to understate the importance of this. In fact, one of our students, Caitlin, became really famous during the Ebola time period for doing something very simple but very useful, which is to take data that was published as PDF files for Ebola and creating a computer-readable data set so that everybody in the community could use. Such simple action has actually made it useful for all the modeling work that went on. Embedded interactions with policymakers is another important thing that we have learned, so that we don't, as scientists, just work in silos in our offices, but working with the folks who are designing and implementing these policies. V&V remains an open question. I think it can take an entire conference, and I think it won't make everybody happy for sure, but I think V&V in this setting is not the same as V&V in a classical physical setting, where predictive aspects really solve much of the problem you want. And finally, I think what we've learned is to develop models that are useful, you have to try and derive requirements by working with policymakers. If we don't do this and use that to constantly refine our models, then in some ways we can publish a whole lot, but I think in the end, it's write-only papers that we produce. And I think that's not the way we would like to work on science if you want it to be useful. So I'll stop here in the interest of time.
Questions?
Very simple, because I'm not literate in these things. First, in your mind, what did you mean when you wrote fundamental limits of computing? And second, what is V&V?
V&V is validation verification.
Sorry for that, I just have to admit my ignorance.
It's a term that a lot of people use, and I wanted to say space. Fundamental limits of computing is, I think, an important question, to me at least, personally, of course, but I think what I'm trying to say here is that we might throw as much computing power as we want, but we have to note and remember that there are fundamental limitations for what can be computed. Of course, at the early part of the last century, we had results from Gödel, which talked about being able to compute or not compute. We have since then scaled it down to what can be computed efficiently and not efficiently, right? Because just not being able to compute was a useful theorem then, but talking about being able to do it within certain time. So back to your question about 0.02 seconds, I say that that's a challenge for us, and there are fundamental limitations in that certain problems, no matter how much hardware you throw at it, will not be computable in that given period of time, at least in the most general form. That doesn't mean you cannot solve it, but then you have to contextualize it. You have to make it specific for that particular problem, and then maybe you produce a solution that is meaningful.
Okay. Another, yeah. Clarification. Coming. Sorry, I'm old.
No, I'm very grateful for what you said. I don't want to go deeply into it now, but I think it's crucial to think carefully about the interface. I spoke very briefly with Bob about it, just as an aside. The interface between the world of computing and, let's say, the world of human beings in a very broad sense, or natural language, and however you put it. I personally would even put it differently. I don't think there are limits to music. You can make an opera about everything, but about something it is silly to make an opera, and it's especially silly to think that you can solve any problem with an opera. For instance, it's hard if you're hungry to get fed by watching an opera. I'm trying to make a trivial remark with a huge implication, which is that from what I see in the world of HPC, there are very few good interfaces with living beings, which is the problem of how we communicate between the HPC world and the decision maker. As Chris said, it's everybody at the end of the day. So we need procedures for that too, and that's something I'm somewhat involved in and interested in. So for that reason, I think your line there was very important. Thank you for that.
Can I say something about that?
Yeah.
There's this.
Only if you switch.
I switched it.
Okay.
So there's this notion of inactive computing, right? Inactive cognition. I'm sorry, inactive cognition. Yeah, okay, so there's the notion of inactive or embodied cognition. You know, it's started with people like Varela and others, but I mean, it's a pretty, although it's talked about a lot, it's actually fairly difficult to talk about even now. But putting computing in the context of the activities that people are using it for adds a richness to the use of it that can't really be understood by looking at the computing as distinct from it entirely. No doubt about that. Still, what we ask the machines to do, oftentimes when you have some bound on something that says this thing's going to blow up and become unreliable and you can't guarantee your 0.2 seconds or whatever, and if you want that guarantee, the guarantee you said, then you have to worry about what he said, okay? That's the problem. And so oftentimes there are dichotomies that if you don't answer the question in general, but you answer the question in a particular situation, then I can guarantee 0.2 again. It's good to know when those things happen. So the combination of this kind of rigorous parsing of our implementations, and also this, what is currently, it'll get harder, it'll get firmer, but a little bit soft maybe, but understanding this embodied cognition version of this, how we're engaged in it, taking it at least into consideration together, I think that is what's going to make this work.
You know, I think that, I'll take 20 seconds and finish, so Alex can go ahead. I think there are limits to computing, much like Shannon's information theory on limit to information. And, you know, as physicists here, you know, Heisenberg's uncertainty principle, which is limit to, you know, a trade-off between the two parameters, H and nu, that he talked about. We have similar trade-offs in computing as well. You cannot do certain things in certain time and space if, you know, if things don't work out right. And these are fundamental limits. They are not limits as to the, you know, you can improve speed-ups by certain constant factor, but these are fundamental limits. And I think they have to be respected, in my opinion, as we start building these solutions.
Okay, yeah, thank you for this first real discussion. And let's move to the next speaker. So thank you again, Madhav.